At the end of video 18, we noted that the law of sines could not be used to help us to fill in the blanks of a triangle of the SAS format, where we were given two side lengths and specifically the angle between them. That's because this data was such that we were never able to fill in 3 out of the 4 blanks in the law of sines formulas. Of course, as well, if we were given the values of all 3 sides of the triangle, an SSS triangle problem, this would also not be possible to solve using law of sines alone, because in this case we are not given any data about the angles, and therefore every possible version of the law of sines would have 2 unknowns in it. So today we're going to introduce the final formula that we use to help us to analyze non-right triangles, and that's called the law of cosines. As the law of sines contained the sine function, the law of cosines will contain the cosine function. So today we should be able to state the law of cosines, and we should be able to use the cosines to help us with SSS triangle problems where all 3 sides are known, and SAS triangle problems where 2 sides and 1 angle are known, and the angle is directly between the 2 sides. So using the standard notation for a non-right triangle, the following formula is true. Suppose that I take the length of the side called C and square it. Then that is almost equal to a squared plus b squared. But because this triangle is not right, because this is not necessarily a right triangle, we need to add an extra term in this formula to compensate for that. So the extra term that we add is -2 times a times b times cosine of the angle gamma. So notice that the angle inside cosine is the angle that's paired with the side labeled C, which is on the far left. Now specifically, this is the version of the law of cosines where C is on the far left side. But there are also 2 other versions, one where a squared is isolated. In this case, a squared would be equal to b squared plus c squared minus 2 times b times c multiplied by cosine of the angle that is paired with the side marked by A. And there's another version where b squared is isolated. B squared would be equal to a squared plus c squared, the other 2 sides, minus 2 times a times c, multiplied by cosine of the angle paired with the side b. So just like law of sines, law of cosines has spaces for 4 unknowns. But what's different here is that we have spaces for 3 sides and 1 angle, not for 2 sides and 2 angles. Therefore, it's possible to use this formula in any case where we have the 3 side lengths and the angle is what is unknown, or in cases where you have 2 of the side lengths and the 1 angle, and the 3rd side length is what is unknown. Let's demonstrate the use of law of cosines on an SSS triangle problem. In this case, and I'm going to draw a quick sketch, not at all to scale, we're given the value of a equals 2, c equals 4, and b equals 3. So it remains for us to find the angles in this triangle. To begin with, I can find the values really of any one of the angles in this triangle. I can even use it to find the angle corresponding to the largest side in the triangle. We don't have the same issue that we had with law of sines because arc cosine, unlike arc sine, actually was able to output obtuse angles. So law of cosines is really nice in that regard. It can even output obtuse angles. So let me go ahead, for example, and maybe find the value of gamma. To find the value of gamma, I'm going to use the version of law of cosines that has a gamma in it, which would be this first version, c squared equals a squared plus b squared minus 2 times a times b times cosine of gamma. So c squared is equal to 4 squared is equal to 16. A squared is equal to 2 squared, which is equal to 4. B squared is equal to 3 squared, which is 9. Minus 2 times A times B is minus 2 times 2 times 3, which is equal to 12. Now, let me work on solving this equation for gamma. If I isolate the cosine function, the first thing that I will need to do is move aside this added 4 and added 9. So 16 minus 4 is 12. 12 minus 9 is 3. Now I need to get rid of this multiplied negative 12 on the far right side, and to get rid of a multiplied number, we divide. Now, applying inverse cosine to both sides, we find that the value of gamma is equal to arc cos of negative 1/4, which, based on my calculator, is approximately equal to 104.5 degrees. Inverse cosine was unique. It was able to produce functions that were as large as 180 degrees. So we have found the accurate value of gamma using inverse cosine. Gamma is the obtuse angle, 104.5 degrees. Beta and alpha. And at this point, I actually have the option to use either law of sines or law of cosines. For alpha, for example, we could use law of cosines, similar to how we use law of cosines to find gamma. To do it in this manner, I would take a squared and set that equal to b squared plus c squared minus 2 times b times c times cosine of alpha. I would use the version of law of cosines that had an alpha in it. So for a squared was 4, b squared was equal to 9, c squared was equal to 16, and then 2 times b times c would be 2 times 3 times 4, which would be equal to 24. So, isolating the cosine, the first thing I'm going to do is take that 4 and subtract a 9 and a 16. Result, negative 21. And then I will get rid of this multiplied negative 24 by dividing both sides by negative 24, and the two minus signs cancel. And now, since inverse cosine is capable of producing any angle that would fit inside any triangle, I can calculate alpha by taking inverse cosine of 21 over 24, and the result is approximately 29 degrees. As rounded to 1 decimal place. Now I have shown how to find alpha using the law of cosines, but at this point in the problem, now that we know gamma, it's also possible to find alpha using law of sines, and most students do tend to prefer this. The first thing that I'm going to note is that alpha is paired with the side a equals 2, and a equals 2 is definitely not the largest side in this triangle. And therefore we can be assured that alpha is not obtuse. It would also be possible to know in advance that alpha is not obtuse because we have already obtained an obtuse angle in this triangle, and at most a triangle can contain one obtuse angle. So let's note alpha cannot be obtuse, and therefore I would be able to find alpha directly by calculating arcsine of something. I'll use the law of sines that has alpha and a in it, a being 2, and now that we know the value of gamma, we can set that equal to sine of 104.5 degrees over c, which was equal to 4. So sine of alpha is equal to 2 times sine of 104.5 degrees over 4, and therefore sine of alpha is approximately equal to, since alpha is an acute angle, we can be assured that alpha really is equal to the inverse cosine of this number is the same 29 degrees that we found via the alternative law of cosines method. Now, which one of these is easier? Which one of these is the easier way to find alpha? I guess that's a matter of taste. Law of cosines, generally speaking, takes a little bit more time. But the thing that I really like about law of cosines is it allows you to temporarily not think about this issue of whether alpha is acute or obtuse. And anything that reduces the amount of thinking that I have to do in a problem, that's something that I appreciate. But it's up to you, whether you want to use law of cosines or law of sines to find the second angle in this triangle. Finally, all that's left is the one remaining angle, beta. And since it's the last angle, it can be found really easily by taking 180 degrees and removing the values of alpha and gamma. So beta's approximate value is 180 degrees minus 29 minus 104.5, which is equal to 46.5. And with that, we've determined all the values in the triangle. Now let's try a really similar exercise. In this case, it's almost exactly the same, except the value of A is a little bit smaller and the value of C is a little bit bigger. So let's see what consequences that might have in terms of the values that we calculate. So maybe to begin with, I will once again go ahead and try and find the angle corresponding to the largest side using law of cosines. So to that end, the largest side is C, the corresponding angle is gamma. So I'll use the version of the law of cosines that has a space for gamma, which says that c squared is equal to a squared plus b squared minus 2 times a times b times cosine of gamma. Now 5 squared is equal to 25, 1 squared is 1, 3 squared is 9, and 2 times 1 times 3 is equal to 6. Now let me remove the 1 and the 9 to the other side. So that's 15 equals negative 6 times cosine of gamma, which means that I need gamma to be an angle such that cosine of that angle outputs the number negative 15 divided by 6. Now, in case you're having trouble visualizing the size of this number here on the left, its decimal approximation is equal to negative 2.5. So what we're asking is for cosine to output a value which is smaller than negative 1. The problem is that cosine of y can't output such a small number. The minimum value it can output is negative 1, and this is less than that. So this is another situation where the data that they have given me corresponds to a triangle that cannot actually exist in real life. There is no triangle with the given side lengths. There's actually a quick way to determine whether or not a triangle can possibly exist with 3 given side lengths. And the rule is this. For a real triangle, its sides satisfy the following property. Each side is smaller than the sum of the other 2 sides. To explain this graphically, lay out one of the sides of the triangle and think of that as a straight line path from A to B. Any other journey from point A to point B is going to be longer than the one that goes straight from A directly toward B. Now, if I lay out the other 2 sides in the triangle, and if I think about following them in sequence, following the first side and following the second side is another way to get from point A to point B. But it's a less efficient way to get from point A to point B. So it's going to take longer to get from point A to point B along these other 2 sides here. As a result, every individual side of a triangle has to be shorter than, has to be more efficient than the sum of the other 2 sides of the triangle. If I look at the data that was given to me in the previous problem, that property is not satisfied by these given side lengths. Note here that 5 is actually larger than the sum of the sides labeled A and B. Okay, to conclude this video and to conclude our discussion of non-right triangles, let's go back to that exercise that we gave at the beginning of video 18. Where we have somebody who walks 4 miles directly south, and then from this position walks 3 miles along a direction which is 30 degrees south of east. So in this picture, the angle 30 degrees would live right here, 30 degrees southward of east. The question is, how far are they from their initial position? If they were to walk directly back to their starting location, how far would it be? So I'm going to reframe this as a triangle problem. I was given the length of one of the sides, A equals 4, and let's say maybe this is B equals 3, and I'm trying to determine the value of the remaining side, C equals question mark, question mark, question mark. Now I was told that the person's second journey was along a direction which was 30 degrees south of east. Now if northward is directly up, east is to the right, south is to the bottom, as it has been sketched in this image, then going from north to east would be 90 degrees. And then we turn an additional 30 degrees toward the south, giving us an angle of 120 degrees in total there. So this would be an example of an SAS triangle problem. I know the length of 2 sides and of the angle between them. So let's see if we can from this determine the value of C. So I'm going to use the version of the law of cosines which has a C in it. C squared is equal to A squared plus B squared minus 2AB cosine of gamma. C is what I'm trying to figure out. I know the value of A, I know the value of B. and I know the value of the angle which is opposite of side length C. That angle, we are told, is 120 degrees. So C squared is equal to 16 plus 9 minus what looks like 24 multiplied by cosine of 120 degrees. So let's quickly get a decimal approximation for this value. So the value of C squared is equal to 37 exactly, and therefore the value of C is equal to the positive square root of 37, which is approximately equal to 6.08, in this case 6.08 miles, since the distances are given in units of miles. So this would be an example of using the law of cosines to fill in one of the blanks in the type of triangle called SAS. At this point, you could continue to use law of sines or law of cosines to fill in the remaining angles if you were interested in that, but that's beyond what was required by the problem. So we're welcome to finish right there. That concludes today's material. Today we introduced the law of cosines, which is a tool that can be used to help us to solve non-right triangles in the SSS or in the SAS case. Law of cosines can be pretty nice because if you're using it to calculate an angle, you can rely on arc cosine to accurately produce even obtuse angles, which was something that the law of sines could not really do.